welcome back to a new video here on the Ludwig Fusel channel. Now in today's video we're going to continue on our journey in DirectX 12. Now what we have done last video is we talked about resources and resource states and how we can modify them with resource barriers to put our resources in a state where they accept drawing. And that's exactly where we gonna head on today with the ultimate goal of actually drawing something. Do we gonna reach the goal? Maybe. Not really drawing, but we're at least gonna see a change in today's video. I'm gonna promise. Now, before we're gonna see that change, I need to frighten you away and say that you're gonna learn 3 new concepts in today's video. Well, DirectX 12, nobody told you it's gonna be easy. It is not easy, it is actually really hard what's going on behind the scenes, but if you understand them, it's actually really chill and really easy and nice and really smart on how it is designed and how it can optimize with these designs and design choices and how well thought the DirectX 12 API actually is. But it needs a lot of work to get there. Now today we're going to talk about the concepts of render target views, descriptors and descriptor heaps. Now, keywords, big keywords. But what are these keywords? Let's quickly summarize them. We're going to talk about render target views, so-called RTVs. A render target view is a descriptor, there we have the next keyword, that describes how a render target, so a target where we want to render to, is laid out. And to place this descriptor, we need to create a descriptor heap, which allocates memory for that descriptor that we can then populate to describe that render target. Alright? Complicated, but actually quite logical. So we're going to walk through these concepts now step by step and quite chill. Now, as you can see, last video we wrote these 2 functions, begin frame and end frame. They took a comment list and were placed in the window to start a new frame and to end a new frame. Now, what did these functions do in the backend? Well, basically what they have done is they introduced a resource barrier on the comment list. In this case, both of the times it was a so-called transition, a resource state transition from the state present to the state render target. Now what this basically means is, hey, take that resource, which is the current back buffer, the current buffer that we are rendering to, which is currently in the state present, and move it to the new state render target. And down here, the other way around from render target to present. And what the result of these 2 barriers is that after that call to begin frame, our buffer is in the correct memory state, resource state, memory barrier state, whatever needs to happen there to be drawn to. However, one important thing, it is currently not the render target. We just altered the state of the resource to be used as a render target, but it is not the render target yet. And down here, we removed that state of being a render target and put it back into its normal state. But we haven't done anything more than just giving the GPU a hint that it needs to change something on the resources. GPU might have not even done something with these commands because NVIDIA decided, no, it's already the right state, I don't need to do something. We don't know what happens. But we basically just currently gave the GPU the hint to put it in a certain state, which is required, even though it might do nothing. But we are not the ones to judge if it has done something. Now what we want to do now is we want to actually render to that. So we want to take that buffer here, that term, and basically say, all right, now use this as the render target. So we want to kind of like say comment list set render target. And as you can see, actually this function exists. It's not directly called set render target, it's actually called OM set render target, but that's actually the thing that we want to do. We want to set a render target. Ideally, we would want to paste that in and everything would work. But that's not how things roll on the GPU. Actually, what that function takes is it takes somewhere down here a const D3D12 CPU descriptor handle. So this function is taking kind of like a handle to a descriptor that describes a resource, and in our case, a certain kind of descriptor that we want to kind of like describe is the so-called render target view. The render target view is a bit of memory that describes how our render target is laid out, because remember, at the end, a resource is just a pointer on the GPU. The pointer, like in C, C++ in general, like on the CPU side, or even like if you have done other GPU programming, if you have a pointer, if you have a void pointer, you can't do something with it. If you have done image programming on the CPU side, to basically know what to do with the image, you always need to know what's kind of like the stride, how wide is a pixel, how many color channels do I have per pixel, how wide is my texture, how high is my texture width and height of the texture. You need to have a certain set of metadata available for this pointer that represents the raw bits of your texture or your image 2D. You need to have this information associated so that you can correctly handle that image. And that's exactly what the render target view is. The render target view is basically a view of the render target. The render target is this resource because it's in the right state. So this is the render target, and what we need to do is we need to set the render target by providing a view to that render target, the so-called render target view. Alright, or good. Now we know what the render target view is. And that's where now descriptors come in place. In general, render target views are abstracted into a higher level concept. We do not only have render target view, there are also depth stencil views, unordered access view, constant buffer views, shader resource views. There are many views that you can use on the GPU that all serve a very certain purpose. And so what they did is they abstracted the view into a general concept of a descriptor, because these are descriptors, a short bit of memory that's describing how the resources are laid out. So in general, a descriptor is basically like the superclass of the render target view that we want to create. And in order to use that functions, we need to provide a handle to the descriptor. Why do we need to have a handle and not the descriptor itself? Well, because the descriptor lives on the GPU. The descriptor is a certain block of memory that resides on the GPU, and that the GPU needs to be referenced and have in its own local memory. So this is why we can get a handle. We can get a handle that exists on the CPU side, and there are also handles that exist on the GPU side. And what we can do is with these handles, we can reference them on the CPU side depending on the usage. If it's directly copied to the GPU and the GPU needs to process the handle, it's going to be a GPU descriptor handle. If the driver or DirectX 12 needs to kind of like process it, then it's a CPU descriptor handle. But at some point, we need to have these descriptors and we need to have them handled to get a handle to it. Now, how are they handled? How are they allocated and created? Well, they are created by the device using so-called descriptor heaps. Now, the descriptor heaps is basically like a malloc for descriptors. A malloc that performs it on the GPU side and on the CPU side and puts some structure in between for management. That's exactly what we need here. So the first thing before we can use these functions, which work with render targets, is we need to get ourselves a descriptor heap that is specifically, in our case here, used for describing my two buffers that I have. How do I do it? Well, it's actually quite simple. Let me quickly comment this out as long as we're not using it. We basically want to create ourselves a descriptor heap. Now it's also a COM pointer, and it's a COM pointer of the type D3D12 descriptor heap. No fancy version, nothing. This is going to be the thing that we want to have, and this is going to be used for render targets, so RTV descriptor heap. That's what we want to create, RTV, render target view. We need to get used to that short term. Now, how do we create this descriptor heap? It's actually quite simple and not that hard. Let's scroll a bit up and maybe put it before we create our buffers. So somewhere here, create RTV heap. Now, how do we create them? Well, we create them with the device. So let's get the device from the context. And the device has a function called create descriptor heap. That's the function that we want to call. It's taking three parameters. It's taking a descriptor and IID PBV args. The descriptor for the descriptor heap. Yeah, kind of like redundant descriptor thing here, but well, we need a CPU side descriptor that describes how our heap on the GPU shall look like. That's then used to put GPU-sided descriptors on it. So yeah, a descriptor for a descriptor. Nice thing. Why do you pop-up Explorer? I don't care. All right, so what's the descriptor here on the CPU side? Oh, there we go. 3D12, descriptor heap desk. That's the thing that we need to do. And sometimes I'm calling this DHD, but heap desk. I want to put this in a bit more readable name here. All right, so we need that thing that we can then plug in here, and then we have IID PPV args to reference that buffer here. Let's maybe put this into a check. So if this failed, let's return false. All right, so now let's populate the descriptor here. So what members are in there? There are descriptor types, number of descriptors, node, mask, and flex. Now, first of all, we need to specify the type. There are multiple types of descriptor heap. There's one heap that can hold CBVs, SRVs, and UAVs. There is one heap that can handle DSVs. There is one heap that can handle RTVs, and there's one heap that can hold sampler. What we need is that one. Of course, we want to have render target view, so the type is going to be RTV for that heap. Now we need to specify the number of descriptors, which is our frame count. So if we have two buffers that we use, we need 2 descriptors, 1 descriptor for each frame that we need. So number of descriptors equals the frame count. Now we have some flex that we can specify. In this case, we do not want to have anything fancy, so we're going to specify none. And then for the node mask, we're going to just set in 0 to use the default settings, because we just have a single GPU that we're going to support. Alright, so now that we have that in place, we should have a correctly constructed descriptor heap, which we of course want to release. So RTV descriptor heap release, it's going to be called here before release our swap chain. And now we should have a heap available. Let's quickly run it to make sure that everything is good. No issues here. Let's Alt 4 out of it. Let's see if we get any errors here. No, we don't get any errors here from D3D12. So this is all good. And now, since we know that our descriptor heap has been created correctly, what we now want to do is we now want to create a descriptor on that heap. How do we create a descriptor on that heap? Well, actually, it is not as straightforward. The heap itself cannot manage itself. The heap is just a block of memory, and as a block of memory, it actually only supports like getting the pointer to it. Now, how do you get the pointer to it? Well, you get this by calling these handles. So actually what you can do is you can call get CPU descriptor handle for heap start, and this is going to give you this CPU descriptor handle for the first descriptor on the heap. We're going to later on talk on how we can actually obtain multiple of these, how we can obtain handles for every handle or for every descriptor in that heap. But what the heap in general supports is just getting the first one. Well, because basically this is just a block of memory, so this is basically just the pointer that has been allocated, but it is a handle. This also works for the GPU side, and same concept. GPU, CPU, same thing. It's always the heap start, always the first descriptor, and kind of like the base pointer of the heap that we just have allocated. Now, how do we then use this? Well, basically, we need to call a function that creates ourselves the descriptor, and we need to provide this function the handle. What is the function that we're going to use? Well, we're going to use it on the device because it is the GPU where the heap is living on, and so we also need to ask the GPU to create it. You could also argue that this could be a function of the command queue, or even like a function of a command list to create a descriptor there. However, the descriptor creation is actually not asynchronously, it seems to be synchronously called. So what you can actually do is you can call a create, for example in our case, render target view. So create render target view. It's a function that we can call on the device, and this now allows us to actually create ourselves a render target view. Now, to create a render target view, we need to provide a resource pointer. We need to provide a descriptor for that render target view. Let's open this up in here. So that one here, D3D12 render target view descriptor. And we need a CPU-sided handle where we want to create that descriptor. So the resource for which we want to create the view, a descriptor, how the view is kind of like laid out, and the handle where we want to place that newly created descriptor. Now, as you can see, we need the resource, so we can actually do it inside of here. We actually need to do it inside the getBuffers function or after the getBuffers function. Let me give you a hint, we're going to do it inside of the getBuffers function because, well, later on if we are recreating the resources, of course, the views need to be recreated as well because the actual pointer changed. So this function should be called within the get buffers, and actually what I want to do is inside of the for loop for every one, I do want to create a render target view. Now very simple, we're first going to provide as the first parameter the buffer, then we need a descriptor, and then we need the handler. So D3D12 render D3D12 RTV, no, how was it called? Render target view. D3D12 render target view. Why? Now IntelliSense is working. All right. So this is basically what we want to create. We want to create that RTV. And then what we need to have is we need to have the descriptor where we want to place it. And this is going to be, again, a bit of an issue. However, what we could do is we could just get the first one. This would actually work. I can just put this in here, and now it would always create the view on the first one. We're going to fix that in a second when we talked about the RTV itself. Now, what does the RTV needs? Well, it needs a few information about how our kind of like render target is laid out. Now, let's peek inside of that so that we know what we need. We need a format, we need a view dimension, and then we have a big union that basically depends on what we provided as a view dimension. So let's start with the format, RTV format. The format is actually the format of our resource or of our back buffer, which has been specified somewhere up here where we described our swap chain. This is the format. Now we need to put it in here as well. So we basically tell this is how the resource looks like. Then we have this view dimension. Now my IntelliSense broke down. That's always good. D3D12 view dimension. Come on. Let's RTV dimension is called. Right. So RTV dimension, and in this case we have a texture 2D because, well, that's exactly what we want to draw to, a two-dimensional image. And then we also need to provide this. So texture 2D is actually a substruct that has something called a MIP slice and a plane slice. Well, MIP slice 0 and plane slice also 0. What is inside of here? We could take a look at this. It is a text 2D RTV, and it basically just consists out of two uints. 0 basically means the first slot. We do not use MIP mapping. MIP mapping is an advanced concept that we're going to talk about in the future. And we also don't use planes in here, so we basically set this also to 0. And this is everything that we kind of like need to describe in here. I told you that you also need to have the width and the height. However, the resource has a bit of metadata associated to it, so it actually can kind of like retrieve this information from the buffer itself. However, the RTV here needs some additional information that the buffer is kind of like not exposing. I'm a bit intrigued that this one is not exposed, but yeah, it's how it works. Basically works like that. You need to describe them and then you can use them. However, this code currently has a big problem. The problem is that we are always going to the CPU descriptor handle for the heap start, which actually means that we 2 times write to the same descriptor, which means that we are overwriting the descriptor. We actually need to advance the handle away from the heap start to the second handle that's in here. And this is not as straightforward as you might think, because this actually involves some fancy stuff. So what I actually want to do is I want to pre-compute these handles. So D3D12 CPU descriptor handle, and then I want to call them RTV handles. And they are going to be a resize of frame count. So what we actually want to do is we want to preload all of these handles that we need and provide them with a correct value. Now, how can we do that? Well, we're going to do this after the initialization of our descriptor heap. So what I want to do here is I want to say create handles to view. Now, how do I create these handles? Well, for these handles, I need 2 things. First of all, I need the first handle. So this is kind of like the first handle, descriptor heap, get me the first handle. And then what we need to do is we now need to have kind of like the size of a handle, kind of like the stride, so that we know how to increment this handle to move to the next handle, or to the second handle, third handle, fourth handle. So how do we do that? Well, actually we can ask our device. We can ask our device to get device, and then we can say get descriptor handle increment size, and this function is going to tell us the number of bytes that we need to increment this first handle to get to the next handle. We're going to provide it a type, and then we can say auto handle increment, and then we kind of like get the increment of our handles. Now we can write ourselves a fancy little for loop to actually now copy the data to our handles that we want to use at some point, and then I can say alright, RTV handles at I equals my first handle, and then I of course need to alter my first handle. Now these handles are actually not, I cannot just say plus handle increment, I can't do math with them directly because they are actually structs. So what I need to do is I need to actually get to the pointer value that's inside of that handle and say this is plus equal handle increment times I, which is now going to which is now on the first handle, adding 0 to the pointer, and the second handle is going to add handle increment, and if we would have a third one, 2 times handle increment. This is basically the math that we need to initialize these handles correctly. So RTV handle is going to be always the first handle, and then it's going to get incremented. So this is how we create handles to the views. Now we have the handles, now we can use them. Now we're going to use the handle down there, where we created that once, and I'm basically going to say RTV handles at position I, and then I can populate the correct handles here. Alright, so this is everything that we need to create ourselves these handles. Maybe let's put a breakpoint in here so that we can see this piece of code is hit, that we don't get any issues, and now you can see it's getting hit. And if I take a look at this, the descriptor is filled, and if you take a look at the handles, you can actually see that we have 2 pointer values that are filled in here with a certain distance between them. And if I continue on here, we shouldn't get any problems, nothing in the output. So if I continue on here, well, everything still behaves the same. Now the interesting thing that we want to do is now we want to use these handles. How do we use them? Well, at the begin frame where we had this om set render target. Now om set render target takes a certain number of handles actually. Now in our case we just want to have one render target. We can actually have multiple of them, and there are reasons. For example, if you do deferred rendering and have multiple G-buffers, you might have 3 render targets bound, and each color channel in each render target would retrieve a different value, which is later on required for rendering. So then you could have multiple render targets bound. In our case we just have one. And this also means that we also just need one handle. So since we can have multiple in here, we later on going to need a pointer of them. And instead of getting the I, we're just going to take the current one and we'll make it a pointer so that we can call it a day. Then we have a Boolean value here. We can actually specify if this is a continuous array of handles, or if it is actually a pointer to an array of pointers to handles, basically. So either a continuous block or kind of like an array of actual pointers or actual pointers to handles. So either this is the first handle, it's going to increment itself automatically, or basically I have an array of them. Now, additionally to that Boolean value, it's also taking a handle for the def stencil descriptor. We're not going to use def stenciling, so I'm going to put this one to null pointer. And if I do it, it looks like that, and this is actually everything that we need. If I now run that, let's see what we got. Well, black window, but actually something going on. We don't get any issues, but actually there is something going on here. We could quickly debug this with a graphic debugger, but we're going to get to the graphic debugger after the next thing that I have announced to you, that we get a bit of color today. And for that, I want to quickly show this to you. Because, well, basically, the setRenderTarget call is not the only call that we can make. Actually, there's another call. We can actually clear the render target view. Clearing render target view is important if we want to put a different background color on the render target, or if we want to be 100% sure that the render target is cleared, which you should always do. So before I'm going to set this one, I'm going to make sure that I'm going to clear the render target. It is a CPU descriptor handle. Why? Yeah, because it's a heap. RTV handles, there you go, now it's correct. And we have a few more parameters on that function. You can see that we need an array of 4 floats and some rectangles to basically provide how we want to clear our render target view. Well, color, we can do it quite simple. Let's maybe separate this like that. Clear color. Let's provide a clear color here that we want to do. For example, everything red would be like that. So this basically means red channel to 1, green and blue to 0, and alpha channel to 1, which means completely opaque. And then I can provide the clear color in here. And actually what you can do is you can provide 0 and null pointer to clear the whole render target. And if I do it like that, we should be hopefully presented with a red render target. And that's exactly what we got. Yay, we got color on the screen. It's now red and your eyes are burning. Nice. We can, of course, mix colors if we want, right? 0.5 here, for example. RG, a bit of green. Now we have yellowy stuff. Maybe a bit too much red. Let's maybe put this like to 0.8. And maybe that one to 0.6, something like that. And let's see what color we get. Yeah, that's an ugly color. I think I want to have quite more blue. Dramatically decrease that one and maybe a bit decrease that one. This should maybe give us a nice color. I don't know. Yeah, that's a nice color that we can use. And as you can see now, we have color on the screen. Because we have a render target view. We have a view of the render target, we can clear the render target, we can set it as a render target, and we can call it a day. Quite some things that we have done. But we have color. We have reached something, finally. It's not a black screen anymore, which is good, so that you're gonna still click the videos and not gonna quit because you're not seeing anything. Clearing render target view, probably always gonna clear to black, but in this case, we're gonna have color so that you see something. Alright, so let's quickly summarize what we have done and why we have done it that way. Now, first of all, we have created ourselves a render target. Now, first of all, we have created ourselves a RTV heap. A heap where we can place render target views as descriptors. We have created this heap with the create descriptor heap function. And we provided a descriptor in here for the descriptor heap. We told that we're going to hold render target views. We're going to put as many render target views here as we have frames, so that we can reuse this descriptor and don't need to recreate them every frame. That's important here. Of course, we could just use one, and we could recreate them with the create render target view function of the device would work, but it's not good because this is synchronously, or it might synchronize under the hood, and yeah, it requires computational power. We want to create it once, so we need 2 of them to hold our buffer count. Then we basically created the view. Then what I have done is I have retrieved myself the first handle on that heap. And since we now have the first handle, we can use the handle increment size to increment it to the next handle, so that we can modify that pointer member here. So I use that for loop to basically create myself as many handles as we have frames and store them in an internal array so I can reuse them later. Now, every time our buffers are created, not if they are released, because we don't need to release views. Views are just descriptors where the resources are. A view shall never point to an invalid resource, so as soon as we're going to use it again, we need to recreate them, which happens at get buffers. And get buffers, somewhere down here, basically additionally to then just only return the buffer pointer, is also creating a render target view on the CPU and pushes this through the D3D12 device pointer to the GPU with the create render target view function, which takes a pointer to the resource and a bit of information on how the resource is laid out, and a handle where it shall store that. That handle is then consumed on our begin frame function in these 2 functions. The first function here is clearing the render target, so we're going to make sure that it is at a certain color value. By the way, it is the correct way around. The render target view needs to be cleared before it has been set, or should be done like that. We just find a clear color here on the CPU side, which was a parameter inside the clear render target view. There's no need for like descriptors for colors, because basically this is like just one 32-bit value at the end. No, it's actually a floating point. I don't know if the driver is converting it to... the driver is probably going to convert it to a 32-bit value that has all the 8 color channels as 8-bit values encoded, but yeah, I wouldn't know. So we provided this on the CPU side, kind of like as a argument to the instruction clear render target view that has been put on the comment list, as well as down here in the OMZ render target 0. You don't need to understand how the signature here works, just one main takeaway here, one view pointer to that handle that is pointing to that view, and the other is the false and null pointer. Same here, 0 and null pointer, because we're not going to use advanced stuff. If you would use this one, the 0 and rechts, you could only clear a certain portion of that render target view, and then we could already draw it, right? We could already draw by just calling clear render target view by always clearing a 1 pixel value to a certain color. Then we could already do all software rasterizing and draw it with the software and just calling clear render target view. But that's not the point of using the GPU to then send everything by the clear render target view function. No, that's not what we want to do. And yeah, that's basically how it works. Now let's open up Nsight Graphics and let's do a quick GPU trace of that. Right, so it should open up any second. For Nsight Graphics, we need release builds. So let's put this to release and quickly build it so that we are on release. That's important. All right, now it recompiled that. There is my project. Let's start this one and take a look on what's happening. Let's click keep here. And there we see it. You can see that I still have my window here with hit F11 for frame capture, and I have my nice background color. I can hit F11 and boom, I have a frame capture. And now you can actually see that if I now take that replay bar, you can actually see that I have multiple events. So if I go to the left, it's black. Then I move it forward. This is basically the clear event that happened. The clear event made it that color, so you can see the change from black to that color. And here on the right, it was kind of like the state where it gets presented. We didn't have any change on presenting, so the final state is the same. So you can see our iterations that our frame went through. It was black, then it was cleared to a color, and then it was ready. Now, of course, we want to take a look at this. If we take a look at this, you can see actually how stuff works. Or not how it works, but at least what they have done. You can see that we have multiple events in here. You can see here's our execute comment list. This is always where we mark the start. Execute comment list. Then we had the clear render target view. You can see the values that I have provided for clearing and the rectangles, as well as kind of like a handle here. And I can even go on the right and take a look at the clear info. I can actually even take a look at the descriptor heap. So if I click at that, you can actually see that I have a descriptor heap in here, which has render target views. Actually, the number of descriptors is not looking good that's in here, but you shouldn't mind that it could be driver incompatibility by it's showing that high number. It's basically 2 inside here, but yeah, you can see that it kind of like still keeps track of that. Because that's CPU handle. But you can see that there's like no, this is just a counter. These values don't seem to be correct. They are all, it is some invalid stuff. But yeah. Or maybe that one here, that descriptor heap might be a thing. Yeah, that's the descriptor heap. This down here were just the handles, and the handles were kind of like unscoped. But this is kind of like the heap that we were referencing, RTV heap with 2 descriptors, no flag, no node mask, so I can actually see all of that looks good. And our texture actually should also be good. If I click around, I could open this up in a so-called resource viewer. You can actually now see that we have here our texture. We can actually take a look at the color values, and now you can actually see that the RGB and the alpha value has been 1-to-1 taken over and put it into the memory locations on the GPU. It's actually not a proper address. It is actually just an offset here. We don't really get access to the actual access here. And we can also get a graphical representation. You can see that buffer here. We can take a look at this. Resource fully initialized and frame are not queryable at frame start. So this is kind of like our buffer that's currently presented, and since it's in the state present and not what's the back buffer, we don't have access to that in Nsight Graphics here. We just see our current one, which is the render target. that one, we're not going to have access to it. We can see it. We can even see here that we have a view to it. I can see this is the view to it, mip/0, format defined. And if we would have multiple views, we could take a look at multiple there as well. Now, down here, as you can see, clear render target view. After that, we had our OM set render targets with the information on what was going on here. We don't get information on that one because that state probably never made it to the GPU because we didn't draw it. So as you can see, some of these events are like colored. Every event that is kind of like colored is kind of like a GPU event. This is a GPU event execute. 11 is a GPU event because it cleared the render target view. It has done that on the GPU. Signaling was done on the GPU. This is red because I think it's synchronized with the GPU. And then we had present, which was also executed at the GPU. So you can kind of like see these difference at the events. These are kind of like also, as you can see, grayed out, the same than like this resource barrier, because they are probably not even hit at the GPU at all. You can't actually even see like a value on the GPU timings for clear render target view, but this doesn't need to mean anything. It probably was executed on a GPU because of the color of its event. But it might also be that it factored this out or it reduced buffers. I know. But yeah, basically clearing doesn't cost time, which is not 100% correct. But in terms of how NVIDIA sees it, it doesn't take time. Yeah, you can see this is a really powerful tool. You can have many, many things that you can take a look at that. You can actually open up heaps. We're not going to have discrete heaps because we didn't use them. However, you can take a look at descriptor heaps and see which descriptor heap was used. This was the heap that we have used. You can actually see that in this heap we have 2 entries, yes, because we have 2 back buffers, one referencing the resource 3 and one referencing the resource 4. One of them currently is not the swap chain buffer, so we don't have access to it. And that one down here, we have access to it if we open this up here again, our nicely cleared color. And you can also see that all of these are kind of like valid, and yeah, you can kind of like see how your heaps look like. These are seems like something that has been allocated by NVIDIA inside redirected CPU handles, but we don't care about these ones. Now, is there something else that we might want to be interested in? Yeah, maybe we can take a look at the API statistics so that you can see a bit what's going on. So this is kind of like showing you which API calls were frequent, which API calls were costly, and how the overall performance in terms of API calls are. For example, you can see resource barriers is the call that we have done the most often. Yes, because we use 2. Down here, you can actually see that actually the most of the time that was costing us performance was the present call because it needed synchronization. So basically what we're doing is we are always sitting there with the CPU and waiting until we have V-blanks to be synchronously with the monitor. So we are definitely not CPU bound and we are not GPU bound. We are currently refresh rate of monitor bound on our application, which makes sense because we're not doing something. If we would already be bound, we would do something completely wrong. But yeah, this is kind of like how you do it. You need to know how this works, how your later on probably way more convoluted DirectX 12 code is gonna be laid out as a series of events on the GPU, how these events execute, how states that you introduce here are required for subsequent API calls, which objects kind of like were affected by the call, and what happened on that. And site graphics cannot tell you that, but it's the most important thing that you know how to use your tools. We're probably also going to use Pix in the future, which is the graphics debugger introduced by Microsoft. Pix has other information available. I tend to like Insight Graphics more, because it gives us more detail on what happens, the on-screen display on our application, the UI that's drawn over it, the frame replay, and debugging. This thing, it is more powerful, as I think, or as my taste is. However, there are a few unique features on Microsoft Pix that has been specifically designed for DirectX 12. that are worth noting, but we're gonna take a look at the graphics debuggers when we are there. There's also one by AMD and also one by Intel, so like everybody has their own thing. It depends on, I have an NVIDIA GPU, so I'm probably most of the time gonna use Inside Graphics because it can tell me the most informations. Right, I can even like go in here and see my GPU options, ray tracing tier, and stuff that we don't care currently about, but it's important. You need to know how these tools work, because at some point you gotta sit there, write code, and think about concepts and write code for like 5 hours, and then you get a black image. And you don't know why, and you change of your values, it doesn't help, and then you quit. You need to know how you use your tools, to take a look at these, to take a look how the calls were redirected, what the state of the resources were, how the resources are laid out, and why there might be nothing on the screen. Graphic debuggers, important. Really, really important. So yeah, we can click resume here, and then we can continue on. And boom, finished. All right, so thank you for watching. Make sure to like and subscribe to the channel. Until next time, have a nice day. Bye.